Welcome to Lecture 11 of Programming Languages. Now, as you read through the lecture notes, we'll talk about the abstract syntax. Now, we're very familiar with concrete syntax, and concrete syntax is what you type in when you program. And concrete syntax contains stuff like semicolons, parentheses, brackets, and other stuff that you're used to, and you have to form the correct syntax. But out of that, we really only need certain pieces of information. For example, if we have an if expression right here, the three pieces of information that we need to extract out of this is what is the test expression, what expression do we evaluate when it's true, when the test expression is true, and what expression do we evaluate when it's false. So it doesn't matter if a programming language requires you to type in ifs like this, or like this, or like this. So every programming language has a parser, and the parser's job is to take the concrete syntax, or what you are used to seeing when you program and type in, is to take that concrete syntax and turn it and extract the important information out of it and turn it into an abstract syntax tree. Now, every programming language has a grammar that describes the concrete syntax. And in Java, for instance, the grammar includes a semicolon after each line. And it also includes the curly braces that you put around functions. In Python, the grammar includes the white space, or the syntactic white space, or the tabs you put in front of functions. And in Racket, the grammar includes all of the parentheses that you include when you type in your code. And so every language has a grammar, and the parser's job is to parse through that grammar and abstract the important information. So over here we've come up with a simple grammar for a Racket-like language. We either have Lambda expressions or application expressions, which call a function, and then we have numbers and symbols. And each one of these expressions has been given a name. So a number is a lit expression, or a literal expression. A symbol, that's a variable reference, is called a var expression. Then we have the lambda expression and an application expression. And if you notice, we have inside of the parentheses the important information that we need to know. Like, what number did they put in? Or what symbol are they using? And in the case of a lambda expression, what are the parameters to the function, and what is the body of the function? In an application expression, what is the function we're going to call, and what is the parameter we're going to pass in? Now, this is somewhat limiting because every function has to have one and only one symbol, but we're just keeping it simple so that we can understand the grammar of this language. Right here is a lambda expression, or one of these expressions that follows this grammar. So what would the abstract syntax tree look like? When you generate an abstract syntax tree, it's a lot like doing a syntactic derivation. So when we see this expression, we do a syntactic derivation starting with this, working our way to this lambda expression. And as you can see from the picture below, we have a lambda expression whose parameter is x, and the body is an application expression. The application expression has an operator, or the ratter, and an operand called the rand. The operator is a var expression with x, and the operand is another application expression. Its operator is another var expression with f, and the operand is another var expression with x. So as you can see, this is a syntactic derivation, but we make boxes around it and label the information like that. And once you've taken your concrete syntax and turned it into an abstract syntax tree, you've basically abstracted the meaning out of the concrete syntax. One thing that you can do with that is translate from one language to another. If you have a program written in one language and you parse it and abstract all the details out, now you know what that program means. Then you can unparse it into another language. In fact, in this class, I used to have a project where you would write some code that would parse a racket program or a program in this language, and then you would unparse it into Java. Now that's a lot like a translation service would work, because if you try to translate English to some other language and you just translate each word, you're not going to get the right grammar, and it was going to get pretty confusing. Some languages put their adjectives in front of the noun, and other languages put the adjectives behind the noun. So in order to translate more accurately, they abstract the meaning as best they can out of the sentences they have, come up with an abstract syntax tree of what they mean by the language, and then they unparse it into a different language, and that's a much better way of doing a translation than translating word by word. Now, using the defined data type from the previous lecture, we can create structs or a data type to hold our abstract syntax tree. So using this BNF right here, we're able to create a data type, an expression data type, for each one of the 4 expressions that we have here, storing the data that we need to store or abstract away from each expression. Now what we want to do is take an expression that's in concrete syntax and create these out of it, or our abstract syntax tree. And that's called parsing. So following our steps of writing a recursive program, step 1, and luckily there's just one non-terminal, is to create a function for each non-terminal. Step 2 is to separate out our productions. So we have 4 different productions. And just so you know, this is the BNF we're working with. So an expression can be a number, a symbol, a lambda, or an application. Now separating these two from these two is actually pretty easy, because if our expression is a number, we know we have this one. If it's a symbol, then we know we have this one. Now both of these are actually a list, and remember, lists are made out of pairs. So how do we separate whether we have a lambda expression or an application expression? So if we have a number, then we know we have a number, a symbol, and a pair will be both of these. So somehow we have to separate out which one. And what we're going to do is look for a symbol called lambda as the first element of this list. And if the first element is lambda, then we know we have a lambda expression. If not, then we know we have an application expression. So if we take the car, if we know it's a pair, we take the car of the expression and we get lambda, then we know it's a lambda expression. If not, we know it's an application expression. Now if it's not a number, symbol, or pair, then we're going to just error. This is a default case. And this is something Essentials of Programming Language package gives us to have a nice error printout when something is not valid. All we need is a symbol, and this is usually the name of the function the error occurs in. This is a string, and it's kind of like printing out in C++. This little tilde s is a little placeholder that we're going to put this expression in that placeholder, so we get a nice error message. And so if we see the error message, if we just give it an empty list, which doesn't match anything in our BNF, we can see that we get that error invalid syntax. Now we can try this with other expressions. So let's try a number, and of course a number is a lit expression. We can try a symbol, which will be a var expression. We can try an application expression with 2 var expressions inside, and that's an application expression. And then we can also do a lambda expression. Then a lambda needs a parameter and then a body. And we can see that it is successfully figuring out what kind of expression we have. Now step 3 is to break apart compound data. Well, a lit expression is just a number, nothing to break apart there. And a var expression is just a symbol, nothing to break apart there. But when we have a lambda expression, we need to extract out the parameter and the body. In an application expression, we need to extract out the operator or ratter and the rand. So if we have a lambda expression, to get that symbol out, and notice that the symbol is in the second position, but it's also inside of a list. So we take the cutter to move to the second element of the list, then we take the car of that and we get the parameter inside of a list, and car one more time gets that symbol out of the list. So this is the symbol in our lambda expression. And you can also go through the box and pointer diagram and see to get the third element out, which is the body expression. That's this right here. So we're going to do the same thing for our application expression. So when we have an application expression, it has two expressions inside of it, and it's a list. So to get the first element out of a list, we just take the car of the list. To get the second element, the cutter moves us to the second box, and the car will get the element out. So here is our ratter, and here is our rand. The fourth step is to make our recursive calls. So this right here is an expression, and this is an expression, and this is an expression. Remember in the BNF that the parameter to the lambda function is just a symbol. So we wouldn't make a recursive call on that. So let's make our recursive calls. So the body of the lambda is another expression, so we're just going to make a recursive call. The body of the application expression has an operator that is an expression and an operand that's an expression, so we're going to make the two recursive calls. Now we're on step 5. What we want to do is call the constructors for each one of these types of expressions when we have it. So when we have a literal expression, let's go ahead and call the constructor to create a literal expression. We'll also do that for a var expression. Remember what we're doing is we're trying to take the concrete syntax, which is inside of these list things, and we're trying to abstract the important information out and build a structure that stores the important information. So that's why we're using this new data type to store the information. So when we have a literal expression, we're just going to create a lit expression. And if we have a var expression, we're just going to create a var expression. Now just ignore these conses right here. I had to somehow close this up so that I can run the code, but I'm not going to test the cases of lambda or an application expression. I'm just going to test these two cases right here. So when we have just a symbol, that's a symbol expression or a var expression, and you can see that it gives me back a struct that has that symbol in it. And if we were also to put a number there, we get a literal expression struct as well. So now let's work on our lambda and our application expression. So when we have a lambda expression, we want to take the ID and the body and construct a lambda expression data type out of it. So all we need to do is call the constructor, pass in the ID, and then pass in the body. But notice we're still evaluating this body, so we can turn that into an abstract syntax tree that can get attached inside of my lambda expression. So we'll test this out. If we have a lambda expression, here's the ID and here's the body. Notice the body is a literal expression with the 5 inside of it. So when I run this, I get a lambda expression whose ID is X and whose body is a literal expression with 5 inside of it. Our last case, if we have an application expression, we're going to parse the operator, the ratter, and we're going to parse the operand, or the rand, and they're going to become an abstract syntax tree, or one of these expression data types. And then we can pack them inside of a new application expression that's going to store them. So as you can see, here's an application expression with a var expression as the operator and a literal expression as the operand. And when we run that, we get an application expression whose ratter is a var expression with F, and whose rand is a literal expression with 5. Now this is the expression that we started off with and had the abstract syntax tree, a lambda expression whose body is an application expression, who has a var expression as the operator, and the operand is another application expression. So when we parse that expression, we get our abstract syntax tree. And that's the same thing that we have here. Notice a lambda expression, X is the ID, we got an application expression for the body, we have the operator, the operand is another app expression, with a var expression and another var expression inside. And that's what we have here, our lambda expression with x as the ID, an application expression with the body, and so on. Now this is going to take in as input one of these abstract syntax trees, and it's going to convert it back into our concrete syntax. And so this parses it, and we get an abstract syntax tree, and then we can unparse it. Now imagine that we just wrote this to unparse it instead of back into our lambda syntax that we started with. We can unparse it into, say, a Java syntax. So let's go ahead and try that. So we're going to parse this lambda expression into one of these abstract syntax trees. Then the unparse is going to take that in as input and convert it back into a lambda expression. So if we run our code and try it, we get this and it returns the same thing. So it doesn't seem too impressive, but what really happened is our code up here parsed through this and made sense out of it. It made an abstract syntax tree with all the important information. And then the unparse took that important information and reformed it back into the concrete syntax. So now for our interpreter, instead of unparsing the abstract syntax tree, we're going to evaluate it or run the code and make our abstract syntax tree happen.